everyone, this is Satish. Today we are concluding our discussion on differential calculus applied to kinematics. And here our purpose is to show that the basic equations of kinematics, which all of you are familiar, can be derived using the concepts of differential calculus. In most of the textbooks, it is done using integral calculus. But we are going to do that using differential calculus, and the technique employed there is very useful in various situations of physics, particularly in analyzing power series of different functions. We will start with the position of the particle represented as a function of time. Therefore, xt, that is the position of the particle, is b0, that is the coefficient, plus b1 t plus b2 t square plus b3 t cube. We are stopping at the cubic function because our purpose is to derive the equations of kinematics when the acceleration of the particle is a constant. And the acceleration of a particle constant is obtained by the quadratic equation, as we have seen earlier. Therefore, I am stopping at this. This b0, b1, b2 and b3 are the coefficients of this expansion, which is called a power series expansion of this function. Any function which is normally used in elementary level physics can be expanded as a power series like this in terms of the independent variable. If it is fx, that will be independent variable will be x. If it is t is the independent variable, it can be expressed as a function like this. And if we extract the coefficients b0, b1, b2 and b3, then this power series is none. So we use the methods of differential calculus for extracting these coefficients. First of all, we notice that at t is equal to 0, all these coefficients b1, b2, b3 involving terms will cancel, and we will see that x0 is equal to b0. Therefore, this gives the first coefficient. To obtain the second coefficient, we take the derivative of this and express v as a function of time, which is dx by dt. And if you take the derivative of this, b0 is a constant that will vanish, and b1t derivative is b1, b2t square will be 2b2t, and b3t cube will be 3b3t square. Here, if we take t is equal to 0, then these coefficients b2 and b3 involving terms will vanish, and b1 alone survives, and we can write b0 is equal to b1. We have extracted the second coefficient. Now we find the derivative again. A as a function of time is equal to dv by dt, that is equal to b1 is a constant, 2b2t when derivative is taken will become 2b2, and 3b3t square when derivative is taken will be 3 multiplied by 2b3t. And here also at t is equal to 0, these terms will cancel and 2b2 alone will survive, and we can see that a0 divided by 2 is equal to b2. That is the third coefficient. If you want to extract the last coefficient, that also can be done by taking dA by dt, that will be equal to 6 B3 and 1 by 6 dA by dt will be equal to B3. Thus we have extracted all the coefficients B0, B1, B2 and B3, and using that we can write an expression for the displacement as a function of time. Therefore, we can replace this by xt is equal to V0. V0 can be replaced by our x0. B1 can be replaced by V0. B2 can be replaced by A0 by 2. And B3 can be replaced by 1 by 6 dA by dt t cube. This is the series expansion of the position function up to third order. Now we can use this to derive the equations of motion. First of all, we take this xt. This is xt is equal to x0 plus v0 is the velocity of the particle at the initial time t is equal to 0, and that we usually call as the initial velocity, and initial velocity usually represented by the letter u. Therefore, you have an ut here, plus a0 is the velocity acceleration at time t is equal to 0, but if we take acceleration as a constant, that is a uniformly accelerated body, then this a0 can be written as a. So this is a divided by 2 multiplied by t square. And when a is a constant, dA by dt will be 0, and therefore this term will vanish. Therefore, this is for uniformly accelerated motion. And xt minus x0, x0 is the initial position, xt is the final position, therefore this difference will be the displacement. And this displacement we usually write using the letter s. And therefore we can write this relation as s is equal to ut plus half at square, which is the familiar equation of kinematics you study in the lower classes. But here the difference is that we have shown that using the methods of differential calculus. And also we can extend that. Even if a is not a constant, you can take dA by dt t cube, and next term will be d square a by dt square multiplied by t raised to 4 plus etc. All those terms can be taken, but that is usually not needed. Most of the questions we have will have a uniformly accelerated motion. If acceleration is not uniform, you can use this series also, but it will be easier to use integral calculus for doing that. Next, we have to calculate the velocity. And velocity v is equal to dx by dt, that is the derivative of this. x0 is a constant, therefore its derivative is 0. U is a constant, therefore ut will have a derivative u, plus this t square will have a derivative 2t, and therefore this 2 will cancel and this will be 80. Therefore, this gives you the familiar equation v is equal to u plus at. Now, we can eliminate the time using this equation and obtain the next useful kinematical equation. That is, we can write t is equal to v minus u divided by a from this, and therefore s is equal to u multiplied by v minus u divided by a plus half a multiplied by v minus u by a whole square divided by a square. One a will cancel and you can take 2a as the LCM, and this will be 2u multiplied by v minus u plus v minus u whole square. And this can be simplified. This will be 2uv. We can simplify this. This will be 2uv minus 2u square plus v minus u whole square is plus v square plus u square minus 2uv, and there is a 2a standing here, so whole divided by 2a. This 2uv and this 2uv will cancel. This minus 2u square plus u square will be minus u square. Therefore, this will be equal to, this is s. That will be v square minus u square divided by 2a. That gives you the famous equation v square minus u square is equal to 2as. We have derived this by taking a cubic equation for position as a function of time, but that can be generalized to an nth order equation and we will get a series. That will give a very general power series which can be used to find the expansion of various functions like e raised to x, sin x, cos x, log x, like that. And that is very useful. But that is slightly advanced level, therefore I am not discussing that. I am stopping with the derivation of this equation. And in the next section, we will start with the integral calculus, basic ideas of integral calculus. Suppose the position of a particle is given as a function of time. That is, we have position of a particle, that is x as a function of time. And we have the velocity of the particle v as a function of time. Acceleration of a particle, this is acceleration as a function of time. Then we know from our previous discussion that if we have a process of differentiation, then we can go from the position as a function of time to velocity as a function of time, and velocity as a function of time to acceleration as a function of time. For this, we need differentiation. Now imagine that we know the acceleration and we want to find out the velocity. For that, the process is the procedure which is called integration. And if we want to find the position of a particle with the velocity given, this process is also integration. So integration is the process in calculus by which we calculate from acceleration we can calculate velocity, from velocity that is just the reverse process. And we are going to analyze how to do integration of a function. Integration can be approached in two ways. Mathematically, integration can be approached in two ways. One, integration as an anti-derivative. That is, as the reverse process of taking derivative or differentiation. Integration is the reverse process of differentiation. Another is, it can also be considered as the limit of a sum. Differentiation is the limit of a ratio. Integration is the limit of a sum. And we will start with this approach. That is integration as an anti-derivative. So we will see how that could be done. That is, how can you integrate, or what do you mean by integrating a function? Imagine that we have a relation fx, that is a function of independent variable x, is equal to d by dx of another function g of x. Then we know that if you differentiate gx, you will get fx. And the reverse process is that if you integrate fx, you get gx. If you know gx, you differentiate and find fx. If you know fx, you integrate and find gx. And we write integral fx dx is equal to gx. This typically is the reverse process of differentiation. For example, we know that d by dx of x square is equal to 2x. Therefore, we can write this 2x as fx. If 2x is given, we can say that the integral of 2x is x square. And the derivative of x square is 2x. So it is just the reverse process. So we can say that integral fx dx is equal to integral 2x dx is equal to x square. So we say that x square is the integral of 2x. 2x is the derivative of x square. That is a reverse process. Now we can see that if we add a constant to this, the derivative will be 2x itself. D by dx of x square is 2x. D by dx of a constant is 0. Therefore, 2x is obtained by differentiating x square plus a constant. That constant can be 0, that can be 5, that can be 8, that can be 100. We can have infinite number of constants. Therefore, we write this as x square plus c. This constant c, which we write here, is called the constant of integration. This c is called constant of integration. And this constant of integration is always written with the function. Therefore, the integral of 2x can be an infinite number of functions. It is not definite. It can be x square, it can be x square plus 5, it can be x square plus 20, it can be x square plus 10,000, whatever it is. They are different functions. So, the integral of 2x has infinite number of functions of the answer. It is not definite. It is to be determined by evaluating c. If c is evaluated to be 5, then it is a definite function. If c is not known, c is arbitrary, then we call this as an indefinite integral. This is called an indefinite integral. We can take another example. Let we know that d by dx of minus cos x is equal to sin x. If this is given, this can be calculated. Therefore, we say that integral sin x dx is equal to minus cos x plus c. Similarly, you can write all functions by taking the functions whose derivative you know can be just reversed to obtain the integral. Therefore, by using the methods of differential calculus, that is the table of standard differentials which we have seen, we can just reverse that and develop a table for the standard integrals. We have found 10 differentials, 10 functions whose differential we have written as a table, and we can do the reverse process and write it like this. So based on that, we can write the standard integrals. If you know the standard integrals of these functions and certain basic rules of integration, which we will see later, using that you can integrate almost all functions which are needed at elementary level physics. Of course, integrating functions is more tricky when the functions becomes much complicated. But usually we have comparatively simple functions. Therefore, we do it one by one. We know that d by dx of x raised to n plus 1 divided by n plus 1. The derivative of x raised to n plus 1 by n plus 1 is n plus 1 multiplied by x raised to n divided by n plus 1. N plus 1 will cancel and we will get this is equal to xn. Using our criterion, the integral of xn with respect to x is x raised to n plus 1 by n plus 1. Our fx is x raised to n and gx is x raised to n plus 1 by n plus 1. So we write this as the first relation as integral x raised to n dx is equal to x raised to n plus 1 divided by n plus 1 plus c. Second one. Here we have to make a condition. If n is equal to minus 1, this will become 1 by x. And we have to write it as integral 1 by x dx. We know that d by dx of log x is 1 by x. Therefore, integral of 1 by x dx will be log x, natural log of x plus c. Third one, we have integral sin x dx. We know that d by dx of minus cos x is sin x. Therefore, the integral of sin x will be equal to minus cos x plus c. Fourth one, integral cos x dx. We know that integral derivative of sin x is cos x. Therefore, integral cos x dx is equal to sin x plus c. 5. Integral sec square x dx. We know that derivative of tan x is sec square x. Therefore, integral sec square x dx will be tan x plus c. Similarly, integral cosec square x dx. We know that the derivative of cot x is minus cosec square x. Therefore, integral cosec square x dx is cot x plus c. 7. Integral secant x tan x dx is equal to secant x plus c, because the derivative of secant x is secant x tan x. 8. Integral cosec x cot x dx is equal to minus cosec x plus c. So, these are all obtained by differentiating the value of what we know from the differentiation. So, we have nan integral e raised to x dx. The derivative of e raised to x is e raised to x itself. Therefore, this is e raised to x plus c. E raised to x is a function which, when differentiated, gives the same number, same function, and integrated gives the same number. It's same function, but with a constant c. Then we have integral dx. Integral dx is 1. Integral 1 dx. This can be written as, this is integral x raised to 0 dx. And x raised to n plus 1 by n plus 1 will be x raised to 0 plus 1 by 0 plus 1, that is x raised to 1, that is x. These are the standard values of integration. Standard values of integration which we can use in developing further integration of complicated functions. Few rules of integration, very few rules. In advanced level integration you require other rules also, but we are only concentrating on certain elementary rules of integration. And when you have to integrate more complicated functions which you do in your mathematics course or in certain levels of physics, you will develop additional techniques or additional rules. Here we are taking only the basic rules of integration. The first rule is integral a fx dx is equal to a integral fx dx. That is where a is a constant. For example, integral 5 sin x dx will be equal to 5 multiplied by integral sin x dx, which is equal to minus 5 cos x plus c. The second rule, integral fx plus gx dx is equal to integral fx dx plus integral gx dx. For example, if we have to integrate sin x plus tan x dx, we write it as integral sin x dx plus integral tan x dx. That is equal to minus cos x tan x plus sec square x plus constant. This will be the integral of this. And the third rule, if integral fx dx is equal to fx, integral f ax plus b will be equal to f ax plus b. For example, if integral sin 2x plus 3 will be equal to, there is a 1 by a here, f ax plus b, integral a function of ax plus b is 1 by a times function of ax plus b. Therefore, this is 1 by 2 minus cos 2x plus 3. This is how integration will be done. And all these integrals which we have seen are definite integrals, indefinite integrals, because we cannot fix the value, because the value of the constant is unknown. Now we pass on to the concept of a definite integral. This also you will study in detail in your mathematics course. We will be taking only very elementary definition of definite integrals. The properties of definite integrals, etc., you will learn in detail in mathematics. So, if integral fx dx is equal to fx, then a fundamental theorem in calculus, this is called the fundamental theorem in calculus. Some people call it as the fundamental theorem in mathematics, but I take it as the fundamental theorem in calculus. Tells you that integral from a to b fx dx is equal to f b minus f a. This is a number, you don't have the integration constant, because fb plus c minus fa plus c, that integration constant will cancel, and this will become a definite number, and therefore this is called a definite integral. For example, integral 2 to 4 x square dx. You have to evaluate this. We know that the integral of x square is x raised to n is equal to 2, x raised to n plus 1 by n plus 1, that is x cube divided by 3. And these are called, this is called the lower limit, and this is called the upper limit. And here you put the lower limit here and upper limit here, and you substitute b in the place of x to obtain fb. So this is 2 to 4, therefore this is 2, this is 4. When you substitute 4 cube is 64, this is 64 divided by 3 minus q cube is 8 divided by 3, that is equal to 56 divided by 3. That is a definite number. That is a definite number. It is not indefinite. That is why it is called a definite integral. Now suppose you reverse the limits. That is, you take this to be 2 and this to be 4. Then we know that you substitute 2 here and you substitute 4 here, then this will become plus, this will become minus, and this will become minus. Therefore, we can write a simple rule: integral a to b fx dx is equal to minus of integral b to a fx dx. If you reverse the limits, you put a minus sign for the integral. And another rule which is useful is this. You take this case, integral a to c fx dx plus integral c to b fx dx. That is, you split the limit. For example, integral 2 to 4, instead of that you take the integral from 2 to 3 and then 3 to 4. Like that. You add an intermediate value limit here. And we know that this is equal to f c minus f a plus this is f b minus f c, and this f c will cancel, and this will become f b minus f a, which is nothing but integral a to b fx dx. Therefore, you have a very useful rule where you can split the limit, split the integral into different parts using this rule. That is, integral a to c fx dx plus integral c to b fx dx is equal to integral a to b fx dx. You have other useful rules of integration limits, but we are not going to take. This much will be needed for us at this level. When we go to slight higher level of physics, you require some more rules. Useful example, that is, in several situations, we will have to integrate the product of trigonometric functions. Therefore, we will see as an example what is integral cos square x dx. And if you want to integrate this, we know the value of cos x, sin x, etc., but not cos square x. Therefore, we have to use the trigonometric identity, that is cos square x minus sin square x is equal to cos 2x. This is simply, you have cos a plus b is equal to cos a cos b minus sin a sin b. You put a is equal to b is equal to x, then this will be cos a plus b, that is cos 2x, cos x that will be cos square x, minus sin x that is sin square x. That is how this is obtained. That is from the sum rule of trigonometry. And cos square x, sin square x can be written as 1 minus cos square x, because sin square x plus cos square x is equal to 1. Therefore, sin square x is equal to 1 minus cos square x. So this is cos square x minus 1 minus cos square x, that is equal to 2 cos square x minus 1. Therefore, 2 cos square x is equal to cos 2x plus 1, or we will write it as 1 plus cos 2x. Therefore, we have the useful relation which is better to remember. Cos square x is equal to 1 plus cos 2x divided by 2. In the same manner, you can write for sin square x also, where you eliminate this. This you write as 1 minus sin square x, that will become 1 minus 2 sin square x, and 1 minus 2 sin square x will become 1 minus cos 2x divided by 2. That will be sin square x. This rule for sin square x and cos square x is very useful in our questions. Therefore, we replace this cos square x by 1 plus cos 2x divided by 2. Therefore, this will become integral 1 plus cos 2x divided by 2 dx. This can be written as integral 1 by 2 dx plus 1 by 2 integral cos 2x dx. That is equal to 1 by 2 dx. When integrated, you will get x by 2 plus 1 by 2 multiplied by cos 2x. When integrated, we will get 1 by 2 sin 2x plus c. Therefore, this will be x by 2 plus sin 2x divided by 4 plus c. This will be the integral. And this method can be used for other product trigonometric ratios like sin square x. So this is a very useful method. Now we work out this question as an example. A particle is at 5 meters from the origin at t is equal to 0. Its velocity is given by this function. We have to find its position. To find position from velocity, we have to integrate. Therefore, x as a function of t is equal to integral 6t square plus 4 dt. We know how to integrate this. 6t square integrate will give 6 multiplied by t cube divided by 3 plus 4 dt when integrated will give you 4t plus the constant of integration c. That is equal to 2t cube plus 4t plus c. Now remember that this is an indefinite integral. For an indefinite integral, this constant is to be evaluated. And the most basic method for evaluating the constant is to substitute the value at some non-instant of time t. And then you will get the value of c. C being a constant, if you evaluate that at a particular instant of time, that will be same always. And here it is given that the particle is at 5 meters from the origin when t is equal to 0. It means that x is equal to 5 meters when t is equal to 0. That is the meaning of that. You substitute t is equal to 0 here, and this is x. X is given to be 5. Therefore, 5 is equal to 2t cube when t is equal to 0 will be 0. 4t when t is equal to 0 will be 0 plus c. Therefore, c is equal to 5. So, by using this is usually called evaluating constant of integration using boundary condition. Therefore, boundary condition means at some instant of time, usually it will be at t is equal to 0. The value is given. Using that value, you evaluate the constant. That is how you convert this indefinite integral to a definite integral. Therefore, our xt now becomes 2t cube plus 4t plus 5. You are asked to calculate the position of the particle at t is equal to 2 seconds. At t is equal to 2 seconds, that is x2 is equal to 2 multiplied by 2 cube is 8 plus 4 multiplied by 2 plus 5. That is equal to 16 plus 8 plus 5 equal to 29 meters. Now we pass on to the next aspect of integration, which is a very important concept. That is integration as the limit of a sum. Differentiation is the limit of a ratio. In the same way, integration is the limit of a sum. Therefore, the next concept is integration as a limit of a sum. We have to find integral fx dx. This is what we have to calculate. For that, we plot that function. X is taken here, fx is taken here. And then imagine that the function is like this. And suppose we take a point here, which we call as A, another point here which call as B. Then we are trying to find out the area of this function, that is this curve between the x-axis and the curve and bounded by two lines perpendiculars drawn at x is equal to a and x is equal to b. And we will eventually show that will be equal to integral a to b fx dx. That is what we are going to see. For that, we imagine this to be divided. Our aim is to calculate this area, and we divide this into two parts. Let this be 1. Let this be 2. And our a and b are 1 and 2. That is, this is equal to 1 and this is equal to 2. Now, to find the area, I imagine a rectangle, two rectangles like this. This rectangle has this area, and this is F1, this is 1.5, and this length is F2. This length I take as F2. Then this area I take and this area I take. We know that this is much far away from the actual area, because this much area and this much area, if you add this area and this area, that will be smaller than the actual area by this much area and this much area. That is much larger. Now, if I divide this into like this and calculate the area of the rectangles, this and this, we know that this extra area has decreased. As the number of rectangles is being increased, the area of the rectangles added together will approach the area of the curve. Therefore, if you increase this interval, you increase this number of intervals, then the sum of the areas of these rectangles will approach the area of the curve. That idea we are writing like this. This area of the rectangle, some arbitrary area of the rectangle, will be this distance, if I call as delta x, and this I call as f at some arbitrary point xi. I can write the area of this rectangle as f at xi multiplied by delta x. That is the area of this rectangle. I take another rectangle, calculate the area, another rectangle, calculate the area, another rectangle, calculate the area, add all of them. Therefore, I have a summation sign here. I is equal to 1 to n, and delta x is equal to b minus a divided by n. This distance b minus a is divided into n equal parts. The length of one or breadth of that rectangle is delta x, and that is b minus a divided by n. If you divide this into 10 parts, that is b minus a divided by 10, that is 0.1. If you divide it into 100 parts, that is b minus a divided by 100, that is 0.01. So, as delta x tends to 0. That is, you are making this rectangle smaller and smaller. Delta x tends to 0. And or you can also say that your n tends to infinity. And then this will approach a limit. And that limit is the area of the curve. And it can be shown that, I am not going to prove it explicitly, I take it for granted that this is equal to integral a to b fx dx. So this integral a to b fx dx is the limit of this sum fxi delta x. That basic definition is not very much useful to you as far as physics is concerned, but in mathematics, when you learn integration as a sum of a limit, those problems are important. But as far as physics is concerned, I am taking this only as a formal definition. Based on this, I can write a very important idea that is very important for physics. That is the definite integral as an area. Definite integral as an area. That is, if you plot a function fx with x and we have an area like this, this is A, this is B, and this area, the shaded area, is equal to integral a to b fx dx. If we are taking a velocity function plotted with time, imagine that we have a graph like this. Time is taken in this direction, velocity as a function of time taken in this direction, and I got a graph like this. This is t1, this is t2. And this area, according to our definition, the area is equal to integral t1 to t2 v dt. This is equal to integral t1 to t2 by dt. And this is equal to integral t1 to t2 dx, that is equal to xt2 minus xt1. We know that this is the displacement. So we have displacement is the area of velocity time graph. This we will use extensively when we learn the peculiarities of graphs in kinematics. Then we will use this extensively. We will take a very simple example. This tells you a very interesting thing. In order to evaluate a definite integral, you don't need calculus. You need only geometry. For example, imagine I have a function fx is equal to x. And I want to evaluate this integral. That is, integral x dx is equal to x square divided by 2. Suppose I want to evaluate this from 0 to 6. Then this is 36 divided by 2 is equal to 80. It is x dx. Now, I don't know how to evaluate the integral. Imagine that I don't know, I am an elementary school student, I don't know how to evaluate it. But I know geometry. Therefore, what I do is, I draw a graph. X and x. For example, let this be 2x. This is 36. I changed that simply to avoid the awkwardness of drawing a graph between x and x. Therefore, I take 2x here, I take x here, I will get a straight line graph like this. This is 0, this is 6. This is 6. If this is 6, this is 2x, therefore this is 12. In order to evaluate integral 0 to 6 2x dx, I simply draw this graph and I need to evaluate only this integral, this area. I don't need any calculus. I simply take the area. And area, I know that half base into altitude. That is half multiplied by 6 into 12. That is equal to 36. Therefore, I can evaluate this definite integral by simply drawing the graph and finding the area. If you have a complicated function, you just take a graph paper, take each point, few points, plot that graph, then count the millimeter squares or centimeter squares in the graph paper, you will get a number. That number will be this integral. So for evaluating integrals, you don't need a knowledge of calculus. You can do it from geometry. But in practice, we never do that. We usually, because we know how to integrate. If a person do not know how to integrate also, he can evaluate the definite integral from geometry. And that is how an area is represented by a definite integral. Another application of this integration, which usually comes, is to calculate the area between two curves. Area between two curves. Suppose you have x here and you have one curve which gives you, let this curve be fx. You consider another curve, let this curve be gx. And you want to calculate, let this be a, let this be b. You want to calculate the area between these two curves. This is very important when you learn thermodynamics, heat engines, etc. You draw the PV diagram and calculate the areas like this. That will be very important. And this is simply, this total area will be integral a to b fx dx, and this area will be integral a to b gx dx. Therefore, the area between curves is equal to integral a to b fx dx minus integral a to b gx dx. This can be written in a compact form as integral a to b fx minus gx dx. That will be the area between two curves. That is another application, to calculate the area between two curves. It is an extension of the concept of area of one graph. Now, we can use integration to calculate the average. Suppose we have a function Vt. The average of V between T1 and T2 is given by, this is very important in various situations when you calculate the average value of alternating currents in AC chapter, etc. You will use this method of evaluating the average of a function, average of a continuous function. Average of a discrete function is the sum divided by number. Here the sum becomes an integral and number becomes the difference between the independent variables, and therefore the V average will be equal to, this is true for any function, that can be the average of fx. For this it is 1 by T2 minus T1 integral T1 to T2 Vt dt. Here this, if it is from A to B, here it is 1 by B minus A integral A to B fx dx. This is the definition of average of any continuous function. Average of any continuous function can be calculated using this method. Therefore, that is very useful. That is very useful and handy. And we will see what will be the average between 0 and t when the particle moves with uniform acceleration. Average 0 to t when A is equal to a constant. We can calculate V average. This we have seen earlier. I have told you that in that case the average will be U plus V divided by 2. That is the average that I have told you earlier. Now we are going to show that. This is T2 minus T1. Here T2 is T, T1 is 0. So 1 over T integral 0 to T V dt. We can write this is equal to 1 by T integral 0 to T V is U plus AT dt. That is equal to 1 by T U dt when integrated will become UT. AT dt when integrated will become half AT square. This is UT plus half AT square, and we have to take this from 0 to t, and 0 will cancel, and therefore this is UT plus half AT square. This will be U plus AT. V dt will be U plus AT dt, and this will be UT plus half AT square. And this A is a constant, that is why we have taken it out, and that will be T square divided by 2. We have to divide this by T. That will be equal to U plus AT divided by 2. That is equal to 2U plus AT divided by 2. That is equal to U plus AT divided by 2. U plus AT is V. Therefore, this is equal to U plus V divided by 2. Therefore, when the acceleration is constant, the average will be the initial velocity plus final velocity divided by 2. That can be easily obtained if you use the definition of average velocity or the integral form of the definition of average of continuously varying quantities or varying function. We will conclude this discussion of integral calculus by showing two simple applications of that. There are two simple applications. The detailed applications, several other applications of integral calculus will come in different situations in several chapters to follow. First is the length of a curve. If you take a curve like this, the length between these 2 points, A and B, you divide this into small segments like this. This is dl. And then the length is equal to integral dl. We will see a simple example. Consider a circle. This is the radius. This angle is theta. Let this angle be d theta. And this is dl. And this is dl. This is dl, this is dl, this is dl. You have to add all of them together. You have to integrate that. And this dl is equal to r d theta. This is the radius r. This is the angle, the relation between the arc radius. It is called the arc radius relation. That dl is equal to r d theta. And theta here, theta is equal to 0. And this radius comes here. I have to take this length, not this length. I want to calculate the length of the semicircle. This theta is equal to 0. This is theta is equal to 180. And whenever we use the arc radius relation, we have to express angles in radian, not in degree. Therefore, this is pi radian. 180 degree is pi radian. Therefore, L equal to integral 0 to pi r d theta. R is a constant that can be taken out. 0 to pi d theta. Integral of d theta is theta. Therefore, this is r theta 0 to pi. This will become 0, this will become pi, and this is equal to pi r. That we know is the length of the semicircle. Now we will give one more application and conclude this. That is, find area. Not the area of a curve under that, not that area. For example, imagine we have a circle like this. This is the center. This has a radius r. I want to calculate the area of the circle. I take a circle having radius x, and outside that another circle having radius x plus dx. Then this area, which I call as dA, is equal to this length is 2 pi x. This distance is dx. Therefore, dA will be 2 pi x dx. And this A will be 2 pi is a constant. Integral. The lowest value of x is 0. that is the lower limit. The highest value of x is r, that is the upper limit, x dx. That clearly is equal to 2 pi multiplied by x dx is x square divided by 2, 0 to pi, 0 to r. This is 2 pi multiplied by r square divided by 2, which we all know equal to pi r square. That is, by using the integral calculus method, you can find the area of curves. This can be done for parabola, this can be done for ellipses, this can be done for complicated curves, provided we know the equation of that. And that is slightly complicated application of, slightly higher level application of integration, that you may study in your mathematics curriculum. And in the next section, we will apply these mathematical ideas to develop the equations of motion, to analyze the freely falling body, and also we understand the concept of relative velocity in one dimension. And that will be the theoretical background for analyzing straight line motion in kinematics. Then we will work out serious competitive examination level problems from the chapter on straight line motion. Few representative problems. I will do problems from elementary level for NEET to very advanced level up to the level of JEE advanced. I will be selecting only few problems because of the time constraints. But you can practice lot of problems of the same type based on that. I will be mostly covering almost all types of questions that have appeared in earlier competitive examinations. After that, we will pass on to the plane motion. That is all in this section. Thank you.